Java code, please.
Thank you. Yeah, thank you very much from my side as well that you're all here tonight. I appreciate it. It's the last talk of the conference. And I'm going to talk about fuzzing Java code, as you hopefully expected. My name is Tobias Ospelt, and sometimes I'm also called Floyd. There's no really good story behind it, but that's just what I am, or who I am. So my co-founder, Martin Schobert, and me, we founded Pentagrade AG. And at Pentagrade, we hack things. So we do penetration testing and security analysis for companies, mainly in Switzerland and Germany. And we have been doing this for a decade already. And this is my main occupation, really. So Pentagrade, pen testing. And apart from that, I'm also lecturing at Zurich University of Applied Sciences. So I'm a lecturer for information security. And as a third thing, I'm also participating with the Cybersecurity Liechtenstein Association. That's where we play CTF, and basically everyone is invited. But one of our main purposes is to prepare young people between 15 and 25 for the European Cybersecurity Challenge, where we play for or in the EU against other countries, and we're basically training the team Liechtenstein for this yearly competition. So these are the main three things I'm doing, information security wise, and as you can see, I just like blue logos basically. So what I'm going to talk about today, first of all, I want to talk a little bit about the tools we're going to see today and who created them. Then I want to do a very quick one slide introduction into fuzzing. So what is fuzzing? We'll look at it from an abstract point of view. And then we're going to look at one fuzzer in particular, AFL. It's a very popular fuzzer by now. And this is going to be much more on the topic and technical. And then we're gonna talk about JQF AFL, which is basically taking the entire idea of this AFL fuzzer, which is very well known and very successful, and take it to the Java side. So somebody took the entire idea of AFL to the Java side. And then we're going to talk about the different bug classes we can find. I think this is probably the most important thing to realize when you do Java fuzzing. So what can you find? And then I'm going to show you JQF SEST. And I'm really looking forward to this part, because this should be closest to what your Java developers do in their daily business. And you can really take home and try for yourself. So AFL is the short version for American Fuzzy Lob. It's created by Mikhail Zalewski when he was working at Google, and it lists about 80 contributors on its website. So there are many forks of AFL, and a lot of people use it for different things, for fuzzing, or at least the idea is used for many different things, to fuzz Python code, to fuzz on Windows, to test things on different platforms and so on. And it's not really maintained by Mikhail anymore. At least there was no official announcement saying, hey, I'm not maintaining it anymore, but there were no more new releases. So now there's AFL++. It's maintained by Mark Heuse, who's also very well known in our community, the IT security community, and a couple of other people. But then when AFL++ came out and all the new features were added there, at one point Google decided, well, we also want to publish the official AFL. So there's now also a Google AFL version, which is, let's say, very basic still, or what the last release of the official AFL was. So all the new features are more or less in AFL++, and there haven't been many new feature releases from the Google side. So there are a lot of forks, as it's very normal for a lot of open source projects. And I just wanted to let you know this is not my tool, but I'm kind of using it a lot. So AFL finds security issues. I think this is a list of projects where it found security issues. And, well, I think they just stopped at one point listing all the different software where security issues were found. So it's very successful, and I think this shows it really well. When we talk about JQF, so the entire thing taken to Java, it was created by Rohan at Berkeley University, and it lists about 6 contributors, so 6 people are involved in creating it and maintaining it. And it's, yeah, as I said, the entire idea of AFL for Java. And there were 2 other fuzzers that also tried a similar thing, but those 2 are more or less already unmaintained, and yeah, I haven't used them for a while. So I think JQF is really the one that was successfully implementing it and is still maintained. There are 2 main things in JQF. One is called JQF AFL, which is really using AFL as well, and the other one is JQF SEST, and we're going to look at both of them today. And JQF finds bugs as well. I have to say it's not necessarily security issues. So it finds bugs, but it's also security issues. So we're going to talk about this later, but the reason why this list is so small, I think, is because, well, just not a lot of people tried it yet. So this list isn't longer. So what's fuzzing? Fuzzing is the process of feeding input into a program. And we do it in an automated way to find undesired behavior. Now, undesired behavior is usually a bug, and noticing that we found a bug, we call this capability instrumentation. So being able to see what the program is doing and being able to detect the bug is done through instrumentation. So for example, for a simple C program, this can mean a crash. Now, if we look at the same concept and from an AFL perspective, we can exactly do this. So we can use AFL, and it's file-based. So it uses a file and it will feed it into a program. And the good thing is that AFL will notice when new behavior is triggered inside the program. So it will know which code paths are taken, and then it's able to prefer interesting inputs for the program. So again, noticing that we have different behavior in the program, we can do that through instrumentation. Now, let's look at a more real-world example. So we have libpng, which is a library to parse PNG files, and we have a picture of a rabbit. We can mutate this picture of a rabbit and feed it into the program, and it will hopefully trigger different code paths inside libpng until we find a lot of different code paths through libpng, and we're triggering a lot of different behaviors, maybe even all behaviors that are there for libpng, until we find this undesired behavior. So at one point, hopefully, we find some bug by inputting something special. Now, this is how AFL looks like. So this is the UI of AFL, and I don't want to talk about all of the details today because it's a little bit big. But on the top right corner, you see the overall results, and we want to talk about that today. So let's go back to this image we had before, libpng. So for libpng, if we had a run which would say total pass 871, we would have been able to trigger 871 different behaviors inside libpng, and unique crash means 124. So we found 124 crashes for libpng. This is just an example. This is a very old version of libpng. So we found 124 crashes inside libpng, and we were able to notice it because of instrumentation. And this is a simple crash. For C programs like libpng, we simply find crashes. Now, there's a third parameter called unique hangs, and it says 221. It means that when we were feeding a file into libpng, 221 different files took too long to process. So AFL decided, well, this takes too long. I want to abort this test. And I just let you know that there are 220 files that take longer than I want to wait. So this could mean it will take a lot of time to process, or just a little bit more than AFL wanted to wait. Now, so far we were talking about C programs and AFL. Now let's take a big jump to the Java world. Now we're talking about something completely different because we're applying it to Java. So of course we don't have libpng anymore, but we have a Java library that is also able to parse PNG files. So we have Java image IO as a target, and we still have JQF that is feeding input and triggering different paths. So the blue part is the same. And we have still unique hangs, so we still know which inputs take too long to process. But what does crashes mean in the case of JQF? That's the big question mark. And I want to answer this question mark by doing the JQF tutorial with you. So there's this JQF tutorial on the GitHub webpage, and I made a small video, and I'm going to explain what we do. So we have this test class that parses a PNG file with image IO. So we have the test class, and we can look into it. We have a add_fuzz annotation. We have a function called testRead. We can feed it an input stream, which is what JQF AFL expects. We give it to image IO and say, parse this as a PNG file. And then if an IO exception occurs, we say, we don't care about IO exceptions. So IO exceptions occur whenever there's something inputted, which is not a PNG file, obviously. So I hope, yeah, we're going on. So we can compile this test class with JQF and a regular Java compiler, and then run JQF AFL fuzz on it, and it will happily take our test PNG file, start to feed it into Java image IO, mutate it, and then hopefully we'll find new paths, which we do on the top right, and the execution speed, as we see, is like roughly 500 tests per second, which is already pretty quick. And we find new behavior triggering inside Java image IO. Now, this was the tutorial. So I thought, why not change the tutorial a little bit? And instead of PNG, let's test GIF files. So I just change all the occurrences of PNG to GIF, and run the exact same tutorial from the JQF website on a different format. Again, Java image IO is able to parse GIF files, and we run it again. And we're finding crashes. So this was, I think, 2 weeks ago, 3 weeks ago, and we're still finding 22 crashes. So we still don't know what crashes are. I haven't told you that yet. But at least we noticed that, well, the tutorial was obviously run a lot of time from the maintainer, and he told Java about all the bugs they found, and they fixed it. But nobody bothered to change the tutorial just a little bit to find new security issues or not security issues or bugs or whatever it might be. So I just want to tell you that it's still very easy to find bugs, whatever they might be, in Java and in a lot of libraries, because nobody is doing it. And JQF has been around for 2 years on GitHub now, and nobody did that. So this is what we get. Now, here comes the solution to the question I had. So what are crashes? It's a little bit disappointing for the security guys of you, but, well, instead of crashes, we only get uncaught exceptions. So because Java is memory safe, we cannot get memory corruptions and our program doesn't crash, but we get things such as index out of bounds exception. So if Java would be a memory unsafe language, we would have a memory corruption, but we don't in this case. So this is not really a security issue, but this is a robustness issue inside your Java code. So as a developer, you probably still want to know about these things, but it's not really a security issue. So as I said, the red part, the crashes, are just uncaught exceptions. Now, when you look at this image, you can still see that there are unique hangs. And in the case of JQF AFL, that's actually the more interesting part, because that's where we find the security issues. So I was able to find 5 different infinite loops inside Java programs by using the fuzzer. So I was able to fuzz the Apache TCAP project with JQF AFL, and I found an infinite loop. So if it would parse my image, my file, then it would just use up all the CPU that was there and will run in circles, and the entire Java process would probably at one point be unusable. I was able to do the same for JUnRAR, a library to unpack RAR files. I was able to do this for PDFbox, which is as well an Apache project. And I was even able to do this for Apache Common Compress. Now, Apache Common Compress, I think if you have to unpack a zip file, in Java, you usually use Apache Common Compress, and this was exactly a bug in the zip archive input streamer. So if you try to unpack my zip file, it would result in an infinite loop, and your Java process will never return. So and the last CV was even in Java itself. So in one of the standard libraries, it's a little bit exotic because it's a riff reader parser, but still, even the standard library of Java had a bug where I was able to trigger an infinite loop where the code would never return as soon as you call it with my input file. So this might have been the interesting part for some of the security researchers. You can find infinite loops, but it's just part of it. But now what I want to do first is take this entire thing a little bit closer to your development lifecycle. So in your company, you're developing Java programs, and usually programmers have to do unit tests. And writing unit tests is probably not the favorite part of programming for a lot of Java developers. So wouldn't it be nice to have at least a fuzzer that is very easy to use and generates very good inputs for your code? And this is now possible because of JQF Zest. So JQF Zest takes the entire AFL approach. So everything we just talked about, being able to trigger code paths, knowing when new code paths are triggered, and using these files, it's doing all that. So everything we just talked about. But apart from that, it's also using JUnit quick check generators, which means we can now not only fuzz Java code that expects input streams, but also all kind of other simple Java types. So the main things of JQF Zest, which are really good, is that it's not only for input streams, but more complex Java types. And it will also understand preconditions. So if you have ever written a JUnit test, then you might have written an assume statement, which basically says, so if you get an input as a test and it doesn't adhere to certain constraints, then please don't run the test. So you do an assume statement at the beginning of the test to make sure that whatever you get is in a valid form. So this is basically to test to skip tests that are that don't make any sense. And the third thing is a Maven plugin. So JQF Zest is completely available as a Maven plugin, which means you don't need to install any command line tool anymore. You don't need to install AFL or JQF itself, but just write it as a dependency in your Maven file, and it will pull it down and install it by itself. So this allows really easy continuous integration. And this might be also very important for continuous integration platforms that can now run a fuzzer. So this was the theory to it. I think the developers might be looking for something like this, which is a little bit more applied. So this is an example from the maintainer of JQF, Rohan, who did a test on a data structure called Patricia try. Now, for this code, it's not really important what a Patricia try is, but we have our add fuzz annotation again, so it just means please fuzz this function. But what we can do now is we can pass a map and a string, and it will automatically know how to generate a map. It will automatically know how to generate a string because we have JUnit quick check generators for these two types, and we don't have to care about that. The fuzzer will just know how this works. So we pass in a map which maps strings to integer and a string, which is just the key. And we assume at the beginning, so here we only want to test maps that already contain the string. So we have this assume statement, and test will try to understand this assume statement and only generate inputs that already comply to this assume statement. So it's very powerful there again. It will put it into the Patricia try. So we will parse the map into the Patricia try, and afterwards it will simply say, okay, I assume or I assert that the Patricia try now contains my key. I mean, this is very basic. Every data structure nearly, if you put something in, then if you ask afterwards, is it still in there? Then it should still be in there, right? So this is a very basic test. But he found a bug, and this is actually a very interesting bug. It's marked as priority critical, and it's still unresolved. So it's still open. It was found by Rohan, the maintainer himself of JQF, and it was reported to Commons Collection, an Apache project. And it says it ignores trailing null characters, which means if we have a new Patricia try and we put in X and we say, is X still in the Patricia try? Then it will say, yes, X is of course in the Patricia try. But if we then put in X \U0000 and afterwards we ask, is X still in there? It will say, no, X is not in there anymore. So this violates every assumption of a developer of this data structure. When you put something in a data structure and you put the second thing in it, then the first thing should still be in there. And this means from an attacker point of view, from an information security point of view, you can, by putting something inside the data structure, you can delete from it. And this, I don't really know what the implications are of this, but as this is a very fundamental data structure, this can be really bad. And it's not only, as far as I know, it's not only present for Patricia try, but they have these problems for some of the other data structures inside Apache Commons. Now the UI of JQF SEST looks kind of similar than AFL. I mean, not exactly, but we again get the elapsed time, so how long the fuzzer was running so far, and it says no time limit. So I didn't specify a time limit, but if you have a continuous integration platform and you want to say, okay, for each build we're doing, please run the fuzzer for 5 minutes, you can do that. So you can say in our continuous integration, we allocate 5 minutes for the fuzzer. Unique failures, that's a combination of everything we've seen so far, everything that can go wrong. So it's uncaught exceptions, it's assert statements, and it's hangs. So we find all kind of undesired behavior in there. And we also get the execution speed, which is very important to notice here. It's, in this case, it's 3 times faster than before. So it's really, really, really quick. So you can imagine, because of JQF is very smart, and it knows when a new code path is triggered, and it's able to feed a lot of inputs. It's very good to find its way through your code that you've written. And the total coverage, the branches, is the same as the path. So it found 579 different paths through your binary or through your code. Now, for this presentation, I thought I need to demonstrate how powerful JQF Zest can be, and I did a run for a certain library, and I was looking for a library, and I thought, why not use a cryptographic library? Because people will notice that when something goes wrong in a cryptographic library, then that's bad. Right. So in Java, a lot of people use Bouncy Castle. Who has used Bouncy Castle before? Oh, very nice. Yeah. So we have a lot of Java developers here. And it's also, Bouncy Castle is in every of your Android phones. So this is not like theory. This is now getting applied. So I tested the ASN1 parser of Bouncy Castle. Now, again, it's not important that you know what ASN1 is, but it's a very fundamental structure. So if you have a certificate on the very basic, it's usually stored as ASN1. So although it might be dir or whatever PEM encoding and so on, but on the basis, it's very often ASN1. So I ran JQF Zest against Bouncy Castle ASN1 parser, and this is a video of how I did it. So first of all, we need to write a test class again. This is just as before. We have add fuzz. We now parse in a byte array. That's nice because we have quick check generators for that. We say parse it as an ASN1 input stream, take out all objects, and if you get an IO exception, we don't care about IO exceptions because we know those can happen. So we only need the test class and the dependency file for Maven. We only write 2 files. The dependency file will say, okay, I'm going to use JQF, please install it. I'm going to use quick check generators, and I'm going to use JQF fuzz. So I just specify my dependencies I need to run this test. And of course, I also need Bouncy Castle, the target I'm going to fuzz. So this is just like regular Java development. And then I can say, Maven, please compile the test class, and it will pull down all the dependencies, which was already done, and then compile them, and it will say build successful. And then I can ask Maven itself to run the fuzzer. So I can say, JQF fuzz, please fuzz this class and this function called test with byte array, and run it. Afterwards, we should get our known UI of JQF Zest. And you can already see in a couple of seconds, because it's going so fast, we find 7 unique failures. So we found seven distinct bugs inside the ASN1 parser in 1 minute, 22 seconds. Now, as soon as I looked at all these bugs I found, most of them, again, were interesting for developers because now the Bouncy Castle developers know how their code can fail, and there were class cast exceptions and so on. But one bug was really interesting because it allowed me to fill up the Java memory and basically crash the Java process by using all memory. So I'm able to send a very small ASN1 input, and Java will try to unpack it and allocate really big arrays for it. And that will use up all memory. And at one point, the Java process will die because it doesn't have any memory left. So again, we have a denial of service condition here. So the real success story behind this is not really that I found a bug, but when I reported this to Bouncy Castle, they were really interested and said, "Oh, this is interesting. How did you find them?" And I supplied them with the 2 files and how to build it with Maven and so on. And they started to use it for their entire Bouncy Castle, or not the entire, but at least they said they use it for other places as well. And they started to fuzz their GPG implementation as well. And I guess they found a lot of bugs as well there. So as you can see, nearly every library I try to fuzz, I find bugs. So I hope I can animate some of you to try this fuzzer. Okay, let's talk about the bug classes. So far, we've seen uncaught exceptions, which are not real security issues usually. We find denial of service issues like using all the CPU, infinite loops, and using all the memory and so on. But I hope that at one point, with more instrumentation, we're also able to find other bug classes. Now, I'm saying this, hopefully we will, because this will probably not be easy to do automated, like everything automated. But as soon as you as a developer know a little bit what you expect from your code, you can do assert statements, and then JQF will try to violate these assert statements, so you will notice bugs. And I think it will be really easy to find bugs by writing very little Java code. Now, it's very hard to answer which kind of bug classes we might find with JQF, but I think there is the possibility that we find cryptographic bugs with JQF SEST simply by, for example, doing differential fuzzing. So we take 2 Java libraries that do crypto, and we give them input generated by JQF SEST, and at the end, it will output the result. And if both libraries have the same result, everything's fine. But if they have different results, then something is going wrong, right? Both implementations should do the same. So I think there might be, fuzzing might improve with this code coverage we have with JQF SEST. So we might be able to find cryptographic bugs. I quickly tried to run witcher-proof, if some of you know that project, with JQF SEST, and I didn't find any new bugs, but really that was just a half an hour test, and I need to do some more testing on it. So maybe we can reuse existing work and just plug in JQF SEST and then find new bugs. Cross-site scripting and cross-site request forgery. These are very, very common web application vulnerabilities. I think this is not a good approach to find these kind of things. I can't imagine how you would instrument your code to find these things. So, I mean, there are probably ways to do it, but it's probably too much work to do. Whereas injections, it depends a little bit on on what kind of injection you have. But for example, an SQL injection, I can imagine that if you, for example, fuzz inputs from a user, and then at one point you get an SQL exception, then you might have found an SQL injection as well, right? So this might be possible. It depends on the case. Server-side request forgery. So server-side request forgery means we can send something to a server, and the server will do a network connection for us to a certain place, which can be a big issue. And I think there's also room there, and I'm going to talk about it on the next slide. And then logic bugs. Can we find logic bugs? Well, we can find logic bugs because I already showed you a logic bug. The Patricia try example is a logic bug. If you put something in a data structure, put something else in there, and the first thing vanishes, then that's a logic bug. So I think the future of Java fuzzing might involve the Java Security Policy Manager. The Java Security Policy Manager is a not very well-known feature of your Java runtime environment, and it allows you to specify a policy that says, okay, the entire Java program we're going to run now is not allowed to open up any network connections. That's just an example. And you might ask, well, but how does that help with fuzzing? Well, I have one example that fits really well, and I'm unsure on how many other examples in the future will fit into this use case. But at least for server-side request forgery, I think the Java Security Policy Manager could help. Because can you imagine Image.io, a library that parses images doing a network connection? Well, you might say, no, I think that's not possible. But actually there were in the past, not Image.io, or at least I don't know that Image.io did it, but other image libraries that when they encountered metadata, they tried to parse the metadata in an image file. And metadata, one of the formats is XMP. And XMP is a format that is in XML. And XML is a format that can have external references to other servers. So there are image libraries that happily open up network connections for you if you supply the right metadata in the file format. So if we have a Java Security Policy Manager that would say an image library is not allowed to open up network connections, then we will get an uncaught exception. It would say, hey, something tried to open up the network connection. Here's an exception. And we would notice during the fuzzing run. So at the moment, Java Security Policy Manager is not really necessary to find the bugs I've shown so far, but at one point we might use it, and there's a lot more testing necessary, and I'm really looking forward to what is coming in the Java fuzzing area. Now, I hope you enjoyed my talk, and I hope I was able to animate some of you and you developers to start using JQF. It's very easy, especially if you use Maven. It's very easy to do a fuzzing run. And also for the security researchers, I hope they can maybe on your next engagement, for example, when you do pen testing. I started doing this because one of our customers, they gave me too much Java code, and I was fed up with looking at too much Java code. So I started fuzzing, and I found bugs in their server, and I was able to use all the memory on their server, and they were very happy that I found all these issues. So I hope some of you will try it in the future, and I can just say, come to the Java world. There are lots of bugs to discover. Thank you.
Okay, thank you very much, Tobias. Any question? Yeah.
Hey, so every time there is a failure or something that crashes, normally while you actually solve the coding issue, you should actually also write probably a unit test to test that specific case. Is there a way to actually record the inputs that cause crashes so that you are sure that you're going to rerun them in the future every time?
Yeah, so I mean, I wasn't able to show all the features of JQF test, but it actually takes an input directory where you can put all the old test cases, and it will start fuzzing from there, and it will notice, oh, this is like already triggering a lot of code passes that are really interesting. So I will use this file as a start, and it will, as soon as it generates new ones, and you get an output directory where we call it corpus. So the entire corpus will be stored for you. Yeah. So you can do that. You can use it as an input for your next run. Yeah.
I don't actually have a question, but you jumped to the conclusion that people didn't try to change the example from fuzzing PNG file to GIF file. It's just that they didn't report bug or made it public that they did, but
I know.
You cannot assume anything about what people are doing with fuzzers, right?
Yeah, you're absolutely right. I mean, that's a big problem in the fuzzing world, especially that, so a lot of people are running fuzzers and they find a lot of bugs, but as long as they're not security issue, they just throw them away. They don't even report them. They don't give it to maintainers. They don't care about robustness, because Well, there are probably various different reasons why it happens. So one is, if you're a security researcher, you're paid to find security issues, not regular bugs. They're boring for you. And the other thing is as well, our entire ecosystem is more and more set up like that, because bug bounties, they won't pay you for robustness issues. Some started to pay you if you just improve certain code, but regular bug bounty programs won't pay you for anything else than security bugs, right?
Thank you for mentioning the Google program, which pays you for submitting security patches to open source code. You can get money from it.
What company? I didn't hear. Just go on.
Okay. Do we have another question? Yeah.
Is input generation of the fuzzer deterministic or every run different?
So that's a good question. So I know AFL++ now has a seed command line. So you can say always start with this seed, so it's deterministic. If it's really 100% deterministic, you should ask the maintainers. But I guess there should also be something similar for JQF. And if it's not, you can just basically change it to use a seed for the random generator. So I think it should be fairly easy to make it deterministic. Yeah.
Any other question? Okay. Thanks again.
Thank you.
Thanks to you all.